part 1 of chapter 5, we covered chemical equations. And in part 2 of chapter 5, we will be covering the rest of mass and volume relationships as well as the concept of a mole. An individual atom is incredibly small, and in order for us to use a meaningful quantity of atoms, we use a concept called Avogadro's number. Avogadro's number is defined as the number of atoms in a 12-gram sample of carbon-12, and the number is 6.02 times 10 to the 23rd. A mole is defined as the amount of a substance that contains 6.02 times 10 to the 23rd particles, or an Avogadro's number of atoms is represented by 1 mole. We use this term, a mole, because it's a tangible amount for human interactions. We can hold a mole of a substance in the palm of our hand, and it'll fit fairly easily. This is also what we use as our phrase, a chemist dozen. We can have a mole of anything, and it's always going to be the same exact number of atoms. We can have a mole of water, we can have a mole of caffeine, we can have a mole of sugar. It's always going to be 6.02 times 10 to the 23rd particles of this substance. This is a concept that we're going to use in order to measure the amount of molecules that we're dealing with. In order to help visualize this better, let's compare it to some common concepts. If we were to have a mole of baseballs, or 6.02 times 10 to the 23rd baseballs, they're going to occupy roughly the same mass as the Earth. If we had a mole of drops of water, these will roughly equal the mass of the ocean. You can see that this number is an extremely large number, but it's necessary to represent atoms because atoms are so very tiny. Each substance that we might have a mole of is going to have a different weight. We're always going to have 6.02 times 10 to the 23rd atoms, but they're going to weigh different amounts. And this is going to be based on the formula mass. The formula mass is the average mass of a formula unit relative to that of the carbon-12 atom. And we can obtain the formula mass for any molecule by adding up the atomic masses for the individual atoms within the molecule. If the formula represents a molecule, often the term molecular mass is used. Every atom has its own atomic mass, and this is specific to each element. We can find these numbers on the periodic table. And when we go to determine the molar mass of a compound, we're going to add the atomic mass of every element that's present in that compound. So for example, if we're going to look at chlorine, the molar mass is 35.45 grams per mole. This means that if we have 1 mole of chlorine atoms, so that's 6.02 times 10 to the 23rd chlorine atoms, they're going to weigh a total of 35.453 grams. Now we can look at a situation which is a little bit more complicated. This is the compound NH3. If we want to get the molar mass for NH3, we're going to have to add the atomic mass of each atom. Nitrogen has an atomic mass of 14.01. In this compound, there's 1 nitrogen. Hydrogen has a molar mass of 1.01. Since there's 3 hydrogens present in this compound, we're going to multiply the 1.01 times 3, and we add them all together to get 17.04 grams per mole of NH3. This means that if we have 6.02 times 10 to the 23rd molecules of ammonia, NH3, they're going to weigh 17.04 grams, or the molar mass is 17.04 grams per 1 mole. We can look at another example using the molar mass for CaCO3. Our calcium is going to weigh 40 grams per mole. Our carbon is going to weigh 12 grams per mole, and our oxygen weighs 16 grams per mole. Now, since we have a 3 subscript next to the oxygen, we're going to multiply that 16 by 3, and then we can add up all 3 of these values together to get 102 grams per mole for the molecule CaCO3. Over the next 3 slides, we're going to look at the concept of solutions. When we dissolve any compound into a liquid, that's called a solution. In a solution, we're going to have 2 major species that we're interested in. The solute is going to be the compound that's dissolved into the liquid, and the liquid is going to be called the solvent. If we compare the ratio of these two, we get a term called the solution concentration. That's going to be the amount of solute in a given solvent. For example, if we were to boil some water to make pasta, and we put salt into that water, the salt is going to act as a solute, and the water is going to act as a solvent. This would be considered a fairly dilute solution. If we just put a little bit of salt in the water, that's going to be a relatively small amount of the salt solute compared to the amount of water solvent. A concentrated solution contains relatively large amounts of solute given to a given amount of solvent. An example of this would be if we took the entire bottle of salt and poured it into the water. It could be so concentrated, for example, that it doesn't even all dissolve. A concentrated solution contains large amounts of the solute. Comparing concentrated to dilute is extremely useful, but these are qualitative measurements. They don't tell us exactly how much of a molecule is in the solution. And we can get more specific using the concept of molarity. When we look at molarity, we're looking at a concentration, and there's 2 values we have to incorporate here. In the numerator, we have moles. This is going to be the moles of solute, or a number that we can translate into the number of molecules of the solute that we're putting into the solution. And then in the denominator, we have liters, which is going to be the volume of the solvent that is used for the solution. The molarity gives us a quantitative measurement for the concentration of a solution. The last set of solution terms that we're going to look at are percent concentrations. Percent concentrations come in 2 facets, either percent by volume or percent by mass. In a percent by volume, we take the volume of the solvent and divide it by the volume of the solution to get the total percent of the solute. If we're looking at the percent concentration by mass, we take the mass of the solute and divide it by the mass of the solution